that role I have, I would like first to say hello, everybody, and enjoy the conference. But before we proceed, I would like to say a few words about the organization. So Grigor Rosso is the general chair of this event, and because we always have the situation that nobody will be, or very few people will be attending the last session, I will take the opportunity to thank the organization, all the orange t-shirt people here as well, who do much of the work, but first of all, Grigor, our PC co-chairs, the financial chair has done also quite a lot. Where's Darko? Yeah. Okay. Oh, okay. Darko. Oh, yeah. The other orange people. So give a big hand to everybody who was organized and did a lot of work to do this. Okay. So let's proceed, and I hand over to Grigor to say the rest of the story.
All right. Thank you, Michael. All right, great pleasure to have you here. Welcome to the 32nd iteration of the Automated Software Engineering Conference. I'm going to tell you a few things, general things about the conference, and then I'll pass it to the PC chairs. So we have yesterday we had 310 people registered, and we expect at least 20 more from 66 countries, the blue areas are where people are from, and if you want to see more precise distribution, there are actually 6 countries with more than 10 participants. And you may have noticed already that this happens on the campus of the University of Illinois, at Urbana-Champaign, which is pretty much the main thing going on here. We are right here in this building, Illinois Union. And if you wonder where is Urbana, where is Champaign, actually there is this street called Wright Street, and we're in Urbana, like 100 meters in Urbana, and in 2 minutes you can be in Champaign. Maybe some of you already came from Champaign. So a few words about this place. So there's a joke, many professors say that they come here for the broad horizons, unobstructed by mountains or skyscrapers. But the reality is that many people were very inspired here, faculty and alumni. Some of the accomplishments that were taking place on this campus are like the invention of the LED, integrated circuit, transistor, PhD meter, MRI, and so on. In terms of languages, JavaScript, LLVM, they were founded or co-founded or co-invented by professor alumni from University of Illinois. And companies like Oracle, YouTube, AMD, PayPal, and so on. Nobel Prizes and Pulitzer Prizes. And I think what is unique about this place is that there is a physics professor who got the Nobel Prize twice in life, John Bardeen. And yeah, and he's the only person who did that. But now let's get into our problems here. So this is the building. This is the layout. We are right here in these 3 rooms, A, B, C. They are separated by artificial walls, and you'll see that the walls come in during the sessions. And the exit is there, also there. I didn't realize that that's open. The one will stay open. The restrooms are right there to the right, and you already saw the coffee place. The reception will also be there. We'll extend a bit that room so we have more room for the reception. You can also go outside if the weather is not too cold for you. Then the lunch will be on the 2nd floor or 1st floor, depending on where you are coming from. Here's the 2nd floor up there in the ballroom. You just have to take stairs and go up there. And if you need some time to prepare your presentation, or if you give an interview, by the way, we have a couple of journalists on site, and they will be very glad to interview you, and we may make some connections. If you need a quiet place for that, we have a room at the 4th floor, and there is also an art gallery right here. If you're not sure where they are, ask the orange people. The reception will be there, and as I said, that room will be extended, and there will be a wall here, so we have plenty of room for the reception. than we expected, and I suppose that there are lots of people still to come. We have an overflow room, the colonial room. Again, the orange volunteers will direct you there. So if you, probably that place would be quieter than this place, so you have options. You can also go outside if the weather allows. There's open bar. Unfortunately, we have a no smoking campus, which means that you cannot smoke, not even outside and not even after sunset. If police officers see you, then they will come to me and say, hey, so please don't smoke. At a glance, the schedule is basically all the meals are here in this building. You shouldn't need to leave the building. So the breakfast, the lunches, and the reception or banquet. So every night there will be something. And again, the orange volunteers will direct you. The banquet will be 10 minutes from here in the Alumni Center. So we are here. Alumni Center is about 10 minutes walking. If you cannot walk, let us know. We can give you a ride. Or if you want to drive, we have, there is a parking lot right here next to the Alumni Center that we can give you a parking permit. So the Alumni Center is a very nice building, has great acoustics, and indeed we are going to have a band performing for us, a cappella band, a choir, and they are great. They got all kinds of awards in the United States, so I expect something very interesting. So please be there, but please also bring your banquet pass, because as I said, we have more people registered than we expected. If you know that you do not need it, this yellow thing, please return it to the registration so other people may use it. On Thursday, we are going to have a tour. We are going to go to the Blue Waters supercomputer, which is supposed to be one of the most powerful supercomputers. I don't know exactly how they measure. There are some units of measurement for how powerful these computers are, with tera, peta, and so on. And we'll have a guide, and they will explain us exactly what's going on there. If you want to walk, it's about a 30-minute walk. Could be a bit long, and the rain may not be on our side. There could be some rain, we'll see. Depending on that, we can get rides. And right after the tour, we'll have another reception at the I Hotel, which is a nice hotel. Some of you may already be there. It's next to the research park. There is the research park in this area over here. It's very close, only 3 minutes. That's really walkable. Now, if you need internet, most likely many of you already have EduRoam. No problem, that should work. Otherwise, look for some network ID with guest that should take you where you need to. If you need a power adapter, there is a box of them. Take one if you need, but they are limited, so take one only if you need one. We have a great group of students who volunteer to help, about 20 from our university and from University of Minnesota. And they are also PhD students. They are great researchers. They publish in this conference regularly, so you can talk research to them as well. They are easy to spot. They are awesome. They also wear these orange T-shirts and caps, and some of them more than one. Don't get tricked. Only the last one matters. So if you see a yellow thing on the top, then they are going to help. It's a great organizing committee. Unless you do it, you don't realize how much work organizing a conference requires. And we had a great committee. I was involved in at least 3,000 messages that we exchanged, but I'm pretty sure there were lots of others that I didn't see. And everybody had things to do on a specific time frame, except two persons, Michelle and Felicia, who were always under pressure. They always had to do something. So Michelle was in charge of registration, Felicia in charge of the website. And last but not least, we'd like to thank our sponsors, many of them here, whose help made the registration fee affordable. So with that, I'm going to pass it to the program chairs.
All right, welcome, good morning. So I'm Maxi Penta. I'm together with Tien Nguyen, one of the program chair of this conference, and I would like to tell you a little bit of story about the submission process, reviewing process, and the accepted papers and the program of this conference. So as usual, we got three kinds of submission for the research track, full research papers as usual, experience papers reporting practical application of automated software engineering research, and short new idea papers. Also, we foresee the possibility of reclassifying a full paper into a new idea paper, but I'll tell you more about this in a while. So about 1 month before the abstract submission deadline, we got the first submission, the first abstract submitted. And then all during April, we got a little bit more of abstract, so not that many, as you can see. Then 2 days before the deadline, we reached 71. Oh, that's not that much, actually, so what's wrong with us? OK, 1 more day, so 24 hours before the deadline, 184. So that's pretty healthy. So we were expecting a few more, but we are on the average, and then when we reached the deadline, that was the final number, and we actually got very scared. Wow, that's a lot. That scared us and also PC member, actually. So after 7 more days, we had the actual paper submission deadline, so we actually started from those almost 500 abstracts. And out of them, 388 were actually submitted as papers. We spent a couple of days to review, to have a look at those papers, to identify format violation, double-blind violation, because as you know, this conference is double-blind, and also papers that were out of scope. And because of that, basically, we desk rejected 20 papers. 1 paper was withdrawn, and we sent to review 367 papers. This was done on May 17th, just a couple of days before ICSI started, so people traveling to ICSI could actually download papers, start to review them. So we had a reviewing period from May 17 to June 22. And after that, we first opened an online discussion. ASE applied a hybrid double-blind model. Basically, every time a review was submitted, then the reviewers could see who the authors were. And during the online discussion, basically reviewers pre-rejected 236 papers, and some other papers went into the PC meeting, and 18 papers were actually pre-accepted. So 113 papers were actually then discussed in the PC meeting that was held on July 8 and 9 in Santa Barbara, at the University of Santa Barbara. And I will take the opportunity to thank Teffy Bultan. He was ISTAP general chair, and he really helped a lot us to organize the PC meeting. So during the PC meeting, we discussed those papers, and 43 papers were rejected. And then we got other 45 papers accepted, 14 conditional accepted, and 11 full papers were reclassified as new idea papers. So just to provide you some more details about the accepted papers, in total we got 65 technical papers accepted, which is 21% acceptance rate. And out of them, we selected 3 ACM 6-off distinguished papers. Those are indicated with this star. This is not US Army. This is actually ACM 6-off distinguished paper. You will notice them on the program. And you will see papers that are indicated with different icons in the program. So this is about technical papers. Then we got 2 experience papers accepted. Out of them, we selected one as best paper because it was also nominated by reviewers as best paper, and this has not been disclosed yet. The winner will be announced during the banquet. And then we got 10 new idea papers accepted, and 9 out of the 11 reclassified papers accepted to shorten the paper and present it as a new idea. The conference was actually a very open conference because, as you can see from this graph and from the related statistics, PC and ERP members had basically the same chance of getting their paper accepted as of the rest of the community. So you can even see results of a proportion test, a Fisher test. There is basically no significant difference between PC member and other people in getting their paper accepted. This is about submission trends. You can see there is a number of submissions growing up over the years, especially for what concern the number of technical papers, and we have this number, which is basically a record of submissions. If you want to see some other figures about the reviewing process, in order to review all those papers, PC and ERP member had to review 1,121 to perform 1,121 reviews, which means more than 600,000 words. And during the online discussion, there were almost 1,500 discussion posts. We did a survey to evaluate the quality of the reviews. Of course, as usual, there were people very happy, people less happy about the review they received. This box plot summarized the perceived review quality on a scale from 0 to 10. And as you can see, the median is 8. We got 100 responses out of all the ASE authors. Actually, more than half of people who responded had their paper rejected. Also, in order to recognize people that did their reviewing job very well, we are going to give some Distinguished Reviewer Award, and they will be announced during the banquet. We decided to award 4 PC members and 2 ERP members. And in this slide, we have further details about the quality of review. So the first graph show you whether the authors felt that the outcome of the paper, so whether the paper was accepted or not, was actually justified by the review content or by the meta review, whether reviewers were qualified to review the paper, and whether they got useful comments in order to improve their work. Some more statistics about the country that submitted papers to ASE. In total, we got 43 countries, and as you can see, US, as expected, submitted the highest number of papers, followed by China, and then Germany, Canada, UK, Brazil, Singapore, Italy, and many other countries. And the next graph shows the number of accepted papers. Actually, those are not real papers, but proportional papers per country, so number of normalized papers per country. So you can see again US, China, Germany, and so on. Okay, so I will let Tien tell you about the submission topics and some more details about the program.
Everyone can hear me? Anyone? Hello? Better? Okay. Good morning. My name is Tien Nguyen. Together with Max, I'm program co-chair of this conference. And I would like to talk to you about a topic that we get submissions and the percentage of the acceptance for each topic. For example, you can see it here. The top topic is testing verification is normal, the number of submissions, software analysis, empirical, maintenance evolution, data mining, and software engineering still is the typical popular topics that's submitted to ASE. And look at the word cloud, you can see that the topic just is software automated, model, program, detection, generation, verification, symbolic is the main topic, is a popular topic in the submission. And regarding the accepted paper in terms of number, the one that submitted many will get many accepted paper, testing, analysis, empirical. However, and you look at the topic that we have in the accepted, it's quite similar to the topic that we got from the submission. Some topics, just program repair, testing, automated, program execution, Android, mobile. We have the topic, we have the dedicated session in the program to dedicate for those topics because the number of submission and accepted paper is high in those areas. In terms of acceptance rate, so I just show you is the number, the literal number of the submission, but in terms of acceptance rate, you can see that the topic that have the highest number of submission might not be the one that have the highest number acceptance rate. So the top three, testing, verification, maintenance, evolution, determining its own rank in the bottom 10 with only 22%, but the one with the knowledge execution, acquisition, and management is 57% with only 7 or 8 submissions. So you get 4 out of 7, that's 57%. This year, together with the Journal of Automatic Software Engineering and Robert Cole, we initiate the first time the journal first presentation at the ASE conference, which means that we take all the publication at the journal, ASE journal, since January 2016. We look at all the paper that published from until August 2017, and we look for the paper that have not an extension of the previous conference work, and not evaluated based on the quality. We invited 13 of them to be presented at this conference, and among them 6 groups accepted our invitation and will be presented in the technical program mixed with other papers. And you can see the icon that's showing the journal first paper in your program, and that's icon. And again, thanks to Bob Hall and Journal of Automatic Software Engineering to make this happening. Regarding the technical session, we have the long one, which contains presentation and question and answer, 17 minutes for presentation, 5 minutes for question and answer. The shorter one for the short paper and near paper has 8 minutes for presentation and 3 minutes for question and answer. And the session is a mix of all the experience, new idea, and journal first paper. We group them in terms of topic, but not in terms of the track, so that you can easily follow and to the topic, reach the topic that you like. And at the end of every session, we have 10 minutes of offline question and answer, where the author with the open laptop can discuss with you, and if you miss at the beginning, you can come and talk to them, and those 10 minutes is dedicated for those informal question and answer regarding the technical research. And finally, in my part, I would like to, all of this work cannot be done with the efforts of, all the program committee members, ERP members, and additional reviewers. So this is a picture we took during the PC meeting in Santa Barbara in July 8 and 9. And 32 of them, including 3 of us, will be 35. And expert reviewer panel was not there, but we would like to acknowledge their efforts and contribution, as well as the additional reviewer. So I would like to, give an applause to all of them for their effort to their conference. And we will select 6 distinguished reviewers, and will be handed out during the banquet. And the next one, I will pass my to David, who will talk about the tool session.
So good morning, everyone. So together with Alex, we are organizing this tool demo track for ASE. Alex unfortunately cannot be here due to family constraints. So we have the following dates. So we have submissions on July 2nd, and then notification July 30, camera ready on September 9. Fortunately, we did not receive close to 500 abstracts. We received much less submissions, so we have 32 papers submitted, and eventually we accepted 20 papers, and we're gonna give 2 Best Papers awards during the banquet. So if you have a tool demo paper, please come to the banquet because your paper may be the one selected for the best paper. And then this is some statistics according to the submissions. So the highest number of submissions in terms of countries includes China, USA, and Canada. And this is the results in terms of accepted papers. This is USA, Canada, and Germany have the highest number of papers accepted in the conference. So this 2 demo papers that have been accepted, we presented tomorrow. So tomorrow will be the oral presentation, and it will be at Illini C, the room on my left. And then the day after that, we will have the hands-on session, also at Illini C. Right, so please come and hear this 2 demo presentation and also the hands-on session. So I would like to thank all the tool demo committee. So they have done a very good work in order to review all the papers and select the papers to be included in the conference. Let's give them a round of applause also. So with that, I would like to hand it back to Grigori.
All right, so we are almost on time. So it's time to start the technical part of the conference. It is a great pleasure and honor to introduce Gerard Holzmann, who is one of the pioneers of automated software engineering. He is most well known for the creation of the spin model checker, where for the first time he demonstrated that you can take real distributed systems and totally automatically verify them, show that they do what they're supposed to do. So spin is a marvelous piece of engineering used by many students and researchers. And as Gerard modestly puts it in his bio, for unclear reasons, he was offered all kinds of awards, starting with being a member of the National Academy of Engineering, an ACM fellow. Spin itself got recognized by the ACM with the Systems Software Award. And Gerard actually spent a lot of his life, right, at Bell Labs, 20 years almost at Bell Labs. And then in 2003, he moved to NASA JPL, where he started a laboratory on of reliable systems, LARS. I visited a couple of times, just an amazing lab. I know people in that lab and the work they have done. And Gerard then moved to a new adventure. Now he has a startup, Nimble, and he will probably tell us a few words about that. So without further ado, I'd like to introduce Gerard.
Well, thank you. So if writing software was easy, we wouldn't be here today. None of you would be here. You would have more enjoyable things to do than to come to conferences. So we do know that writing software is hard. In some cases, it is more important to get it right than in other cases. There are many cases where you can just afford to give it your best effort to write reliable code, find the bugs, do all measures of testing that you can think of, be as rigorous as you possibly can, and then hope that the customer that will use your software will not find too many problems. That is not always a good solution. Sometimes it really has to work. If you think about this particular situation where you write a software for a robotic system that has to perform, first time that the software executes about 30 to 40 million miles away from Earth, where really there is no hope of intervening, even if you could see that something is going wrong. There's absolutely no chance that you have to correct the situation, to debug something if the one-way light time is 20 minutes. So just to maybe show you a little bit of what you may have seen before, like the landing sequence of the Mars Science Lab Curiosity rover.
We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Heat shield has separated. We're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for batch shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
So now you see the relief of the people in the control room when the software actually works. So there's about 2.8 million lines of code that drives the rover and the whole system that brought it to Mars. And as I mentioned, the first time it executes in an environment that is fairly poorly understood, the atmosphere, the conditions there, wind conditions, the precise events that will happen during a landing sequence, which must happen completely autonomously at a great distance. You saw all those people in the control room being somewhat nervous about the consequences of something going wrong. You have to realize that there's absolutely nothing they can do. By the time they get the signal, the real events have already taken place 20 minutes ago, either a crash or a proper landing. The system itself was designed to operate for 2 years. And as I showed, the landing was in August 2012. It's now 5 years later. The system is still operating, and we hope it'll operate for a good while longer. So how was the software developed? So just a little snapshot of how this is done at JPL. There's continuous integration for the software built on this particular mission. It's a nightly build. There are about 3,000 calls to the compiler, compiling different parts of the system. There are about 200 modules that go into the software system. Then there's static code analysis that we did to find defects as early as possible. And we had a coding standard, and we did static checking for coding rule compliance. We used a number of different tools for that. First of all, we just used the GNU compiler. That's not the flight compiler. So the flight system is for a PowerPC system, PowerPC equivalent, a RAD 750, radiation hardened PowerPC, basically. But the software is written in a portable manner. May seem unusual for an application, but it's actually an important thing to do. So we can compile it with GNU-CC turning on all warnings in pedantic mode, and our coding standard says that there should be no warnings from the compiler even in that setting. Then we run a bunch of different static analyzers, some research analyzers and some commercial analyzers, Coverity, CodeSonar, and SAML. And we look for bugs, we look for defects or inconsistent code. All the data that is collected every night over the 2.8 million lines of code throughout the development of that software goes into a code review database where it's available to the developers for code review. The total analysis time is about 15 hours, or towards the end of the preparation for the mission, it was about 15 hours, and we run as much stuff in parallel as we can. So the idea of a nightly build start getting stretched. As you know, like these analyzers and developers don't like to work during the day, so the 15 hours, you can't expand that much longer if you throw in more code. So every mission so far has used more software, control software, than the mission before it. So the missions after this one will start, exceeding 3 million, 4 million lines of code easily. And now there's going to be a problem that the static analysis will take too long. Compilation itself is maybe 40 minutes for this code, but to run all these analyzers takes a good deal more time. So now think of this scenario, which is an actual scenario, something that really happened. In February 2012, there's a few months after launch, with the spacecraft on its way to Mars, a bug is discovered. There's an in-flight anomaly, and a manual analysis reveals that there is a function that expects an argument, a parameter of type array with 16 elements, and there's a caller to that function in another module that passes an array of only 8 elements. Now, clearly, that's a problem. It can lead to data corruption. It is caught and it is fixed, but now the question in the next team meeting is where else in the 2.8 million lines of code is this happening? Because if it could happen in this one case, it can happen in other cases too. And now you can say, okay, everybody look, so there are about 40 developers, 30 to 40 developers on the flight software development team. You say, everybody look in the code that you own, if this can also happen. And fix it. The second thing you do is say, okay, let's develop some new checkers for the static analyzers and see if we can catch this automatically. Then you wait 15 hours, and meanwhile, there's a ticking time bomb there. If it happened once, it can happen again. And if it happens just the wrong way, you can lose the spacecraft. So having to wait first for the new checkers to be written, if you really want to be sure that you catch all these cases, and then waiting for the analysis to run, that may be just a little too much time. Now, this is exactly what we did at the time, but it now makes you wonder, like, there should be a better way, right? I should be able to sit down at my terminal, start up the system, and type a query and try to figure out, can I find this just interactively? I want to spend maybe a few minutes on that, maybe in the review meeting itself. Sit down at your terminal and type a query and say, where else can this happen? So first, why does it take 15 hours? So we have, first of all, there's a whole lot of code, right? And it all has to be analyzed. So there's pre-processing, there's lexical analysis. A whole lot of stuff is done to prepare for static analysis, parsing the code, building the abstract syntax tree, the control flow graphs, building all kinds of tables, the symbol table plus all kinds of other tables, doing pointer alias analysis, all that stuff for some of the checkers that may need that particular piece of information. And when all of that is done, you run all the checkers. And plus, every static analyzer has its own data structures that it needs to build. And then, at the end of all that, you run your extra check, so 15 hours later. So now here's a really, so all that time is spent over there. So now here's a really dumb idea. What if you skip that? Right? So, okay, we're spending all that time there. Let's not try to think real hard about how we can make that faster, because somebody would have thought of that already, right? We have parallelized everything that we can, and most of the static analyzers can parallelize their internal algorithms. So let's say, skip it, but we have an extra check. Let's see if there are some really basic types of checks that we can run even before that. Just do lexical analysis. That's sort of the minimum you have to do. You can do that very fast. And you can also parallelize that very well. You can, if you have enough CPU cores, you can take every file and do it in parallel, or every function, and then later combine those results. What if we could do that? So that led to this idea for building this tool, COBRA. It's just basically that idea, like probably this is not going to work, because there's not enough you can do if you just stick to that really basic level of analysis. But let's see. So take the source code, do lexical analysis, populate a database, and build a tool that can query that database. So you can sit at a terminal, that's the idea, like you want interactive response to every query that you can think of. And interactive, with interactive, I mean a response within less than a second. So my query from a few slides ago, I want the answer in less than a second. So what does the database look like? The database is a data structure, and it is a data structure that is exceptionally simple, really pushing this idea to the limit. So it's a stream of lexical tokens. It's a linked list. There's no branching. It's a linked list. That's it. Now, so here's an example of just a program with a main routine. So there's a type, int. There's an identifier, main in this case. There's some syntax for round braces, etc. There's a type name. There's a keyword switch at the end. There's one thing that the lexical analyzer for this tool will do is that it will pair braces, round braces, square braces, curly braces. It will insert a pointer for every brace pair from one to the other, so that the brace pairs define ranges in the lexical token stream. But that's pretty much all it does. It remembers the level of nesting of all these elements, but basically there's some annotation to the tokens, but it is a token stream. Now, the fact that it is a single token stream actually is extremely useful for a number of reasons. One is it's exceptionally friendly to caching. If you want to interrogate or query this linked list very fast and in parallel. Caching is very friendly because the token stream is written sequentially. That means that you can read it sequentially, and you read in whole chunks of the time into the cache and you query that. You can parallelize it easily because you can chop up this big stream into segments and query it separately. So what can you do with this? So the whole thing is this even remotely useful? Because this is so basic, probably there's nothing much of interest that you can do with this. One is you can look for a specific token. Oops, wow, how did I do that? I went all the way to the end. If I wanted to do that, I couldn't, but okay. Okay, I did that. Okay, so first, the obvious, you can look for a particular token. Here's the invocation. You can many things you can do from the command line, but of course the main thing is that you can start it up and then query things in interactive mode. But this is from the command line. Here, optionally with C pre-processing enabled. One other thing I should mention is that since we're just doing lexical analysis, it is very easy to retarget this for other languages. So built into the tool is support for Ada, Java, Python, C, C++, and I think there were a few more that I'm not thinking of right now. Putting in an extra language or your own language is just defining mapping from text strings to lexical token categories. Like you can say, this is an identifier, or this is a keyword, etc. And then you have the whole framework available. So CPP says pre-process the code, type an expression, a token expression, and you'll see in a second what that means. Say I want to find every occurrence of an identifier I, say a variable I. Really bad idea if you define a global variable named I in your code, because you can't find it later, right? If you want to grep for I in your code, you are not going to see what you're looking for, but in this way, you do. You get exactly all the token names I, and those are exactly the variables named I in your code, even if you use them as global variables, which itself, as I mentioned, is a really bad idea, but it works. So that's the obvious. Now, slightly less obvious, you can define patterns, which are really regular expressions. There are two forms implemented in the tool. One is called EXPR, which is a full-blown regular expression with all the bells and whistles that you have. And there's a version called pattern, or PAT, which is a simplified version of a regular expression that is much easier to use with code. Because, you know, round braces are round braces rather than meta symbols of a regular expression, etc. So here a pattern as the example, looking for functions where malloc is called and not free. So it's just a regular expression that says, let's see if this pointer works. Is there a pointer here? So here it says open curly brace, start of the function body or start of any block. Malloc occurs, so dot star means anything, I don't care what. So it's the clean star and the dot for matching any token at all. So this is matching tokens, not characters or strings. Then I see a token named malloc, which is an identifier, and then negation sign, not free, any number of tokens that are not equal to free, and then the close of the block. Now this is already useful, right? So it's just a regular expression, but I can already find interesting types of code. Here's another one saying, is there a switch statement that doesn't have a default clause? Very, very similar, of course. So here's switch keyword, round brace, anything there in the expression in the switch statement, curly brace, no default, star, close curly brace. So now there's one objection you can raise to this, but at least one objection you can raise to this, and it says, what if switch statements are nested? And the nested switch statement has a default clause, but the upper level switch statement does not. And I'll come to that in a second. So that you can't easily do that with a regular expression, and that means you need a little more in the framework to handle those kinds of things. So then you can do name binding. So here, and again, it's very straightforward, right? There's no magic here. So here, for instance, I can look for a type in a block, particular block. I look for anything, then a type name, like int, short, whatever. Then an identifier, so a variable is declared of a certain type. I bind the name. Bind the name of the identifier to X. I pick any name, X. And then I check whether X appears in the rest of the body, the rest of the block where it's declared. If it doesn't appear, that's a problem. Now, the compiler will warn you about that as well, but just to give a few examples of the types of things you can do. So this is sort of to suggest that this might be interesting. Right? So now, because the parser, the lexical analyzer for the tool will match braces, if you type pairs of braces, round braces, curly braces, or square brackets this way, the tool will make sure that they match, right? So they're at the same level of nesting. It's not the first curly brace that it sees in the token stream after that point. It is the matching brace, which is extremely useful. It means that you can actually write these patterns and they work, they do exactly what you hope they would do. So that gets me to interactive query commands, which you can also provide online to handle cases like the one that I just mentioned, where two switch statements are nested. The one with a lower level of nesting has a default clause and the upper level does not. So that example, I want a query sequence that lets me find switch statements in the code that don't have a default clause, even if there may be nested versions that do have a default clause. So here's an example. Here's the query sequence that I give to solve this problem. And again, this is interactive. So let's see. First, I want to find all the switch keywords. So I say mark switch keywords. So this works with sets. And you'll see in a second how that works out, like how all that makes sense. So I say mark all switch tokens in the sequence. Now these are commands, query commands. So now there's a semicolon. That's the command separator. And I say, next, move to the first curly brace after that point. So I have a mark point in the code, say, pointing at all the switch statements, and that could be thousands. So I'm marking those tokens, and now I move that mark point forward to the first curly brace. So that's the next command. I think I have that overview here. And then I say, now I have a range, right? Because these things are paired by the lexical analyzer that defines a range of tokens. So by pointing at the opening curly brace, I have a range of tokens that I can query. And I can query that range and say, does that set, so that range, contain no default statement? And so these are qualifiers. So I say an absence of a default statement at the top level of nesting. And that's exactly what I have. So that gets me this match in the spin code. As you know, most coding standards will say switch statements must have a default clause, and so there's a violation in the spin code of that rule. And so this executes, even though I did this from the command line, this is a relatively small piece of software, it's about 40,000 lines of code, but including the lexical analysis, so this command, entire command, the thing between the quote marks executes. After the lexical analysis completes, I timed this, and it is a fraction of a second. So that means if you have a few million lines of code, of course, building the data structure will take some time. And I'll show you some examples of that shortly. But once you have that data structure in core, you can start typing queries at it, and they all take a fraction of a second. So this now also works for nested switch statements. So here's the context. Get source code in, build the database, type queries at it, and you get patterns of interest out. Very simple to parallelize, as I mentioned. You can split up this linked list, this token stream, into separate segments and process them in parallel. For instance, the example I just gave you, mark all switch statements, you can do that in parallel. So if you have 8 cores, you have each take 1/8 of the token sequence, and they do their marking, move tokens forward, etc. If you have 32 cores or 128 cores, same thing. And it's cache friendly, etc. It'll be very fast. Then, now we have the query language. So that is the second part of the problem. First, build a database that you can query. Now the question is, how do you query it? What kind of language do we need to do this querying? So there are 3 different ways. I've already shown you 2 of them. One is this regular expression-based pattern matching algorithm. One is the online query language, where you give commands, move match points forward, etc., or backwards, and resolve queries that way. So here's an example. Of course, you can, with the command language, of course, you can name scripts. Here's a definition of a script called find with 2 parameters, f and g. And the problem I want to solve, which is actually a real problem I had to solve in some code that I won't mention what it was because I'm not supposed to, where the question was, after a certain point in the execution of this code, dynamic memory allocation should be impossible. So there should be no more calls to any routine that has the string alloc in it, or like malloc. So once you get to this particular point, can you still do dynamic memory allocation? This is how you solve that in this particular query language. So I define a script. First, there are some predefined things, like things that you do a lot, so there's no point in typing out the full command sequence for each one every time. So the predefined command functions. Identify all the functions in the code, all the function definitions, and point to the name of the function definition. Another one, so that one I use here. Another one is build the function control graph. Now, it builds the function control graph, assuming that you don't use function pointers, which you're not supposed to do anyway. Now, of course, we all do anyway, but so this will give you the function call graph using only the information that it has available without doing pointer alias analysis. But so here's that script. So first we identify all the function definitions. Then we move the mark forward to the start of the function body with the next command. Then we query that range and say, does that range, which is the function body, contain any token, an identifier called G, which is a call to that function G. It has to be there if it calls that function G. Then, so now I'm at that curly brace. I have to move back to the function name to remember all the functions that call G. And I put it in a set. So this says store those marks in a set. And now I say clear the marks, reset all the marks. So I'm showing you abbreviations of commands where you can also type the full name of the command, but that's no fun, right? Use abbreviations. Reset and say compute a function call graph of F, store, and now take the intersection with the earlier set and I have it. That's exactly that. So for this particular problem, I can say from, say, function server, can I still call malloc, either directly or indirectly. Like the function call graph shows me the function call graph with F as the root. Right, function call graph with F of the root. Right, so now I can see, can I call any function that calls malloc? Now this is, of course, not flow sensitive. It just says, gives me a worst case. Like, is there a scenario conceivable where I can get to dynamic memory allocation and I display the results? So it's already slightly more powerful than you would suspect. So now the predefined operations on sets include saving something in a set, restoring something from a set, taking the set union, set intersection, or subtracting two sets. Two additional sets are used for storing the current set of marks and the previous one. And that means that since I'm storing the previous one, an undo is just switching these two sets, which means very fast undo, but only a one-level undo. Now, okay, finding dubious code fragments. Here, I'll give an example. Say, think of the 2.8 million lines of flight code. Or if you want a more extreme example, take all the code in the distribution of Linux 4.3, which is 18 million lines of code. So here I'm saying, well, okay, let's do this on 8 cores. I have a list of all the file names, the .c and .h file names, which is easy to collect from the Linux distribution. About 39,000 files. 39,000 files using 8 cores, 84,111,645 tokens in that sequence. Now, of course, reading that in, building the data structure takes a bit of time. But once you have it, you should be able to do interactive query processing, and you can. For instance, is there any if-then-else chain, if-then-else-if chain that doesn't end in an else? So there's a coding rule in lots of standards, including the MISRA standards, the JPL coding standard. Lots of other standards have that. It's similar to every switch statement must have a default clause. If you have if-then-else-if, there should be an else at the end. Otherwise, you might have a missing case, right? An accidentally missing case. The pattern that you can use, here I use the inline version of the pattern rather than the command line version. Works exactly the same way. I look for an else token followed by an if token, then anything in the condition, so then some compound statement, and after the last one, there is no else. And of course, this will find it in under a second over 18 million lines of code. And again, the braces are matched. Here, is there any function definition that is not void? So it returns a value, and we don't care what kind of value. So we just say the type is not void. So it could be any other type, but it's not void. By the end of this, I've figured this out. Any function name, anything in the parameters, and there's no return statement. Now, if you can query that, just type these in, and in under a second, you get all the matches. You won't get all the mistakes, but you get a very good fraction. For very fast response time, this can be quite useful. Checking the sanity of for statements. Now, there is some consistency in the use of for loops, right? And it says that if in the conditional of the for loop, you do a less or less than comparison, probably the control variable of the for loop has to be decremented at the end, or it has to be incremented towards that bound at the end. So here, the pattern that I type is find a for loop, and this is the control body of the for loop, and note again, the braces will match. Anything in the initialization clause, semicolon, so now that's a real semicolon, because this I typed inline. Anything here, then I must see one of these relational operators, followed by anything again, so this is in the conditional part of the clause, and then in the increment part of the clause, I don't see an increment operator. So if you run this over that Linux code, these are two of the matches that you find. So one is in this memtest code, so Linux 4.3. You see, okay, here's ASE compared to upper bound uint max, and in fact, I is decremented. So now, it's probably not incorrect, but it's very sleazy, right? This is really, it counts on a wraparound of the variable, which really you shouldn't write code like that. It's probably on the file, well, you would know, yes. And here's another one. Now again, this is also probably not incorrect, but here I have a comparison against an array, and I decrement the array index. So now whether this works correctly or not depends on the contents of that array. And again, this is not really how you should write code, because it's not obviously correct. It might very well be a bug here. So if I can type these things and get these matches and then look at these matches, if you can do this very rapidly, that increases your productivity enormously. So a little bit about the matching algorithm. So this is just regular expression matching, but we really want it to be fast. So now there's a blog that Ross Cox wrote. Ross was working at Bell Labs for a few summers. Later, after he graduated, he joined Google to be part of the team that produced the Go programming language. But he published this column about 10 years ago about regular expression matching algorithms. Now, when I started implementing this algorithm, I was thinking, well, I need something really fast. Regular expression matching algorithms are really old. They date from the 60s. So I should take advantage of all the research that has been done in the last, whatever it is, 50 years, and implement really the fastest known algorithm that we have available today. But I stumbled upon this column that Ross wrote, where he compared the algorithms that are currently implemented in many languages, he says, including Perl, and he compared it against the regular expression matching algorithms from the 60s, the way they are implemented in tools like awk and grep, the Unix tools. Here's a measurement on a particularly nasty regular expression where he compared the runtime of the matching algorithm between two versions of the expression based on a parameter n, ran it with the version implemented in Perl and with Thomson's original regular expression matching algorithm. And you see that the older algorithm actually behaves much nicer. It doesn't have this sudden blow up at the end. So that led me to take Thomson's algorithm and implement that. And yet that's Ken Thomson, almost unrecognizable in that picture with very short hair and no beard. Dennis Ritchie standing next to him. Thomson's algorithm, as an example of how that algorithm works, here's a pattern for finding expressions with multiple side effects. And again, so this could be a case. So if the side effects apply to the same variable, it could be a case of undefined behavior. So here, the way I type this one is I have a range. So square brackets include options. So either a minus minus or a plus plus token, followed by no sequence point. So no semicolon. I could have added a comma as an optional sequence point. Followed by another one of these pre or post increment or decrement operators, star.c. And the star.c could be 18 million lines of code or more. Now here's a match that I would find, or that you would find in the Linux 4.3 code. Now in this case, it's just illustrating it, and just that matches the expression. There's no sequence pointing between the two increment and decrement operator. In this case, it's fine because they're two different variables. But if the two variables were the same, then it would be a problem. Now, I could actually get that. I didn't think of that, but I could have, of course, get the match, get the side effect on the same variable by doing name binding on, but yeah, okay, so you can extend that expression to get more precise. So Thomson's algorithm is described in this paper that he published in the Communications of the ACM in 1968. If you have a chance, if you want to read a paper that is actually enjoyable to read, that is crystal clear, it is short, it is deep, it is fundamental, and it's just wonderful. Read that paper. Give that paper as an assignment to your students. How do you write a technical paper? It's 5 pages, and it has, I think, 5 or 6 figures in it. There's really a minimal amount of text, but it pins down the technical details precisely and crystal clear. So I read this paper, implemented the algorithm, and so from that expression produces this non-deterministic finite automaton. Now, I like non-deterministic finite automata because we use them in model checking all the time. So to get this into a tool like this is icing on the cake. So translate it into an automaton, and then you execute the automaton to find the matches, and you find them real fast. So last query method that I didn't talk about yet is an inline program. Now, with the query commands that I discussed, or the patterns, there are still certain things that you cannot do that you may want to do. And so for that, we have the query language. And for me, it's partly exploring this space to see what can you do with a tool like this. How do you design a useful language for querying code at this level of detail? So I developed this inline language. So here again, the limiters for identifying an inline program. And again, you can type these interactively, or you can put it in a file and read them in from a file. This is percent open curly brace and percent close curly brace. Anything in between is a program. By default, and this is true for all query commands, the programs are executed once for every token in the sequence, in the inline sequence, which seems a little bizarre, but this is precisely what we want. Like if I say mark all switch statements, that mark command is executed by rushing through the entire linked list, right, from beginning to end, or for the fragment that your core has available to it. So it goes from beginning to end in the linked list, or the section of the linked list, and then marks all those tokens. So the same thing is going to be true here. I write a program that is executed once for every token in the sequence. Now I can overwrite that in that language, but that's the basic idea. So here, just to illustrate what capabilities you have in this language, here's a function definition. The function takes parameters. And here I compute a factorial just to show that, yes, you can do recursive functions in this language. So, and at the end, there's a print command. And then, so this is by default executed once for every token, unless I say stop. Now here, I don't want to compute the factorial for, in this case, if I do it for 10, I don't want to do that for every token in the sequence. Like if I have 800 million tokens, I don't want to compute the same thing 800 million times. So here I say stop at the end, and then it does it only once. And so yes, you get that answer, which is the correct answer, happily. Now if you go 20 factorial, you don't get the right answer, but that's not the problem of this language. That's the problem of the hardware and limited precision in the hardware. So maximum value you can represent in an integer. So we have recursive functions, which means we have a pretty powerful language. An inline program can access any token attribute. So as I mentioned, the lexical analyzer prepares every token with certain attributes. That includes like the function name that it appears in, the file name, the text of the token, the type of the token, like identifier, keyword, etc., modifier, qualifier, etc. Level of nesting of round braces, square braces, curly braces, the length of the token, the line number it appears on, whether it was marked in the current set, sequence number, range, number of lines in the associated range, and then the next token in the sequence, previous token in the sequence, a jump to the end of the range if there's a range like curly brace range, and anything you bind to that token with the inline programs. Now, even simple inline programs can do moderately useful things. So here's an inline program that just goes through the sequence and remembers the token with the longest text. So .len, dot is the current token, .len is the length field of the current token. Remembers that. The variable that I set, so this is typical for scripting languages, that it is untyped, meaning type is derived from context. Now, many of you will not like that because you can't do type checking here, but it's extremely convenient. So you don't have to declare anything, and usually these programs are simple enough that it is obvious what the type of a name is. So here I introduce the name Q, and the parser for the inline program has to figure out what is the type of Q. Now, because I follow Q by a dot, means it is a token reference, and it remembers that. Okay. Now, so at the end of the scan over all the tokens, Q points to the longest identifier. Now I can print that with the print command. Longest identifier is Q.text. I remembered the token. It is this long, this many characters, and then I say stop. So that's already useful. Now, there are also associative arrays. Part of this is inspired by awk. There are associative arrays, and you can use external commands. Before I show this, like the problem I want to solve now is to find the most common token type trigrams. Now, why would you want to do that? Well, because you have to give a talk about the tool and explain what types of things you can do. There's no other sensible reason for doing this, but I just want to show, yes, you can do this. So here, there's two pieces of the program. First part says, you have a particular token, and we're going to go through the whole token sequence and say set Q to point to the next token, R to point to the token after that. So now I have 3 tokens in a row. If all 3 have a type, then I remember that by incrementing associative array with the 3 types as an index, and I call it trigram. So do a count of how many of that particular triple I have seen, and that ends. I think I have this annotated here. So that's an associative array. Then I want to post-process the result. So before I print the result, I say divert the output into a temporary file. Now, if I execute this on 32 cores in parallel, I want to unify all that data, all the counts, onto a single CPU, so I can start doing post-processing on, say, CPU 0. So I say, if you're not CPU 0 for the second part of the program, then go away. But if you are CPU 0, collect all the data from all the other cores, and then print the counts. And now, of course, this is going to print all the counts. So now I have this diversion done so that I can stop the diversion and say sort that array and show me the 10 highest count and remove the array. And I get that output. And so now this long-standing open problem has been solved. It's like, what is the most common type of triple of token types in a typical C program? It's an identifier followed by an operator followed by an identifier. Big surprise. But, so, I mean, the capabilities of the program are fairly serious. So now, you're all thinking now, hopefully, but yeah, but I still can't solve my problems with that. Like with a real static analyzer, is flow sensitive, it builds the abstract syntax tree, it has the control flow graph, it can be a little bit more precise. This is true, but only to a certain point. So here's an attempt to define a flow sensitive property, which I just have the lexical token sequence, should be a challenge, right? So, but because I have recursive function calls in the inline programming language, I can actually do some of it. So here I look at all the source code for the Unix version 7 of the operating system. And I want to do a depth first search to find uninitialized variables. So now this is flow sensitive. And here's one of the results that I get before I tell you how I do it. So here's a program, cat.c, so the implementation of cat in version 7 Unix. You see there's a declaration of def. Now it is set inside this conditional clause, but that's not necessarily, it's a conditional clause, so it could be skipped. And then it's used here. So it means that's a potential use of an uninitialized variable in the Unix source code. Now, note also that in the lexical token sequence from here to here, I must pass that point where def gets assigned a value. So I have to be flow sensitive here to a certain extent. So what this does, and so this is output from scanning 159 files, 30,000 lines of code on one core in less than a second. So this includes the parsing, preparing the linked list. I get 5 accurate warnings and 1 false positives. DFS uninit first creates the obvious links in the code to get some control flow information. It interprets gotos and if then else statements. And of course it can very easily say, you can skip this piece of code optionally by adding in extra pointers into the linked list. Right? So now actually we have a structured linked list where we see a little bit more of the program structure. And then I can do a depth first search in that information for every function call, and I can find these kinds of things. And the whole thing is I can find it very, very fast. Okay, so does it scale? So the whole point was I want to be able to get 2.8 million lines of code sucked into core, type queries at it, and get response times in under a second. So here, to get a more extreme example, again, I took the Linux 4.3 distribution, 18.6 million lines of code in about 40,000 files, and I'm going to check for 2 types of queries that I mentioned before: if then else if chains, if then else if change without an else as the final part of the sequence, and a switch statements without a default clause. And I do the query processing on between 1 and 32 cores. Now, there are 2 parts to this, as is obvious. One is building the data structure and one is querying it. The query processing should be interactive, under a second. Reading in the code and building the database should be fast, but it doesn't have to be interactive. It would be nice if it is, and it is for like programs up to about 200,000 lines of code, but not for millions. So if I do the Linux code on 1 core, it takes a couple of minutes to read that in and to build the lexical analyzer data structure. If I start using multiple cores, if I had linear scaling, I would see this line. I'm not seeing that, and of course we never do because life is not that friendly to us. We see this, and there are some bumps here. It goes down to about 20, 25 seconds to build a data structure for 18 million lines of code, which is reasonable, right? So 20, 25 seconds is something you can wait for. Then the query processing, once the data structure is built, this is the responder. So on 1 core, it takes a couple of seconds. It may take 4 or 5 seconds to answer a query. But as soon as I'm down to 4 cores or more, 4, 6, 7, 8 cores, there's another funny bump here. I have interactive response time. So this is 1 second response time. I want to be below it. If I use more than 4 cores, and almost any system has more than 4 cores, or at least 4 cores now, I have interactive response time. Now, which means, yes, it works, up to even that size. So let me just show, if I can figure out to get this started, just to show you that I'm not making this up, or not completely making this up. I'll do it here for the Linux source code. But first, I put all the file names in this file. It has about 40,000 file names in it. I I read them in. So this part I shortened a little. I don't want to make you wait 25 seconds for this. It warns, because I'm not doing C pre-processing, so it warns you that certain brace pairs are not matching because, you know, of the if-def code. And I'm typing the queries, and you see it is truly interactive, the response zone. So here's it. I was looking for switch statements without a default clause. There's one that it found. When you display it, it also pops up a little window. There's a TickleTK window where you can browse the surrounding code more fully. Okay, that's what I had to say. You can find documentation, manuals, tutorials, binaries on this website. And if you experiment with this tool, I'm very curious to know about your findings. If you find bugs, and I'm sure there are bugs, please do let me know. Thank you.
Oh, thank you. I was actually wondering if you can do incremental analysis as well. Say the code itself is changed. Can you also run the queries interactively?
That's a very good point. So now, one form of incremental analysis is building analyses on top of each other. So one thing you can do is you can pipeline these COBRA calls. So you can say, find all function definitions that have this particular feature. And that streams into the next invocation of COBRA. That's not what you're asking, but I'll get to that. And query that code for this particular extra feature. So that you can do. Another version of that is that you have these sets. So you can say, query all this and put that in one set. And now query something else and put that in another set. And now do union or a differencing of these sets. So that form of multiple and different analyses that you combine results you can do. What you're suggesting is not something I implemented now, but it should be possible because you simply have this token stream. And if you say, well, this program or this piece of the token stream changed, like drop that out and put a new version in, that would not be hard to do that. So say this file changed. Remove all tokens from the data stream that have that file name and add lexical analysis for the changed file name and now redo, keeping the old results, etc. Yeah, should be possible.
So that's very interesting. There was a slide you showed us about reachability analysis. But you also said currently the tool does not do any point analysis, alias analysis. So does it handle interprocedural, some sort of interprocedural analysis like detecting dangling pointers?
Well, so there are two things I should say about this. One is, so I could say no, and that's not the point of the tool. The point of the tool is, and that's not the answer I'm going to give you, but I'll just go through this part of the answer first. Tool is for doing really basic things that you should be able to do interactively. For the more sophisticated things that require pointer alias analysis and interprocedural analysis, you should use a tool like CodeSonar or Coverity or SEML or Clockwork, one of the real commercial tools, and you pay a nice ransom for those, but they're very, very good. However, so the other way to answer that is the COBRA tool sees the output of the lexical analyzer. That's also what every other commercial static analyzer sees and what the compiler sees. What you do with that information is up to you. So you can write a C program and link it to this that does pointer alias analysis if that's what you want for the queries that you want to be able to type interactively. All these things, the additional analysis are going to slow you down, right? So that's cut out from the basic tool because I don't want that slowdown. But if that's the piece that you need, you can build that and add it. You can build it as an inline program, put it in a library, and invoke it when you need it. So you can do everything that the regular compiler can do too, because you get exactly the same information. The token stream that you have is all the information of the program. Nothing is omitted. All the information is there. So yes, you can do that.
That's very exciting. Thank you.
Can you hear me? Okay, good. So my question is like, for me, it seems that your main focus is about developing a query language which can facilitate the developers to flexibly define their static checkers. And that is pretty cool. I'm thinking about, I'm curious whether you have thought about leveraging the same methodology to define some query language to facilitate the static analysis using this control flow or data flow. It's kind of essentially the same thing. With your like regular expressions, you already have all the material there. What you need to do is to define a query language to facilitate the definition of this checkers. How about this control flow information? Is that doable?
Yeah, excellent point. That should be doable. So now there are some tools that do some of this. SAML is a good example. The tool SAML also works by creating a database that you can query with more than SQL-like language. Very powerful, much more powerful than this, but also slower. Like building the database is much slower, and etc. So this is trying to find this balance between how much information am I going to pre-compute and how much information do I leave to the user to add. But what you're saying, yes, you can pre-compute things that are useful for simplifying those types of queries as well. And so you're willing to pay a small price, say this is the domain I'm interested in. I'm not interested in the full-blown data structures that normally get built and that take all so much time to build. Right. Just give me this part and then I query on that. Yes, absolutely.
Thank you so much.
Hello. So, hi. That's a very powerful tool. It's amazing. I used to use Emacs for doing refactoring of C code when there were not refactoring tools for C. So it's amazing. So one question that I have is that do you always need to pre-process and before using COBRA? And if you do, why? Because you are not parsing, right? And so if you don't, do the tokens have preprocessor information? Because that would be, I guess, nice to know if something is coming from a macro or configuration.
Right. No, pre-processing is optional. And for instance, the example I gave of the Linux code, I just blindly made a list of 40,000 .c and .h files in the Linux code. I have no idea how they should be pre-processed properly, but I can query them anyway because I don't, by default, there's no pre-processing. I can tell it to pre-process, but then of course I have to know the right directives to do that correctly. And of course I will miss parts of the code that are conditionally compiled in other settings. Right. So in basic mode, it does no pre-processing, and I have access to, so now the pre-processor directives become available as tokens. So sharp define becomes a token, and the type is CPP, like it's a pre-processing token, and I can query macros, etc. in the same way, because it's just uninterpreted at that point.
Oh, great, thank you.
There are questions over there. I think on this side, the microphone is now working. Okay. Yes, I was afraid somebody would ask that question. So I have to repeat. So coming back to the question that I started with, this problem that was found in the Mars Science Lab source code during flight with array bounds not matching between the call and the function declaration, can I express that in COBRA? So the sequence of events is like that particular experience led me to think, well, there has to be a better way. And of course, a year passes, building the tool and refining it and extending it, et cetera. And okay, now we're here. So, okay, can we do that? You can get close. It's not a matter of typing one line and getting it. You can write, so I did write, but only in the last couple of weeks because I've now gotten this question more often than I should have thought of, you know, that is the obvious question that people are going to ask. So yes, you can get close, like within a few minutes of querying, you can get a short list of all the possible problem points. Like for instance, of course you can create a list, find all the function definitions that have an array in the parameter list, array reference. So in C, arrays are always passed by reference and never by value. So you can easily find those things, and then you can find all the calls to that. You can get the bounds on the arrays in the function definition easily by looking at what's between the square brackets. And now it's a little harder to figure out the thing that gets passed to the function call if that has the proper bound. But at least now the amount of work is reduced quite a bit, so now maybe you get to look at 20 of those and by eyeballing it, making sure that yes, this is okay or not. But yeah, it's a really good question. So I would wish there would have been a one-line answer to this. And if there was, it would have been on a slide. So here I was counting on you haven't forgotten about that first example by the time I get to the end.
One more question and then we can take it.
That's the question over there?
So I was thinking about a graph of cost and benefit, and I was thinking down at the COBRA end, the cost of setting up the queries is real easy. At the spin end, the cost of setting up a query is understanding the domain and writing the promella. And I was thinking of the runtime cost of COBRA and the runtime cost of spin. And I was thinking of the nature of the bugs found by things like COBRA and things like spin. And I'm just wondering if you can tell me anything about that space.
Well, yes, excellent observation. Of course, what COBRA focuses on is potential bugs, and they won't be very deep. So it won't be like a long interprocedural chain of executions. They're fairly shallow types of bugs. Now, in experience from most of us, the really nasty bugs are often shallow. They're very rarely deep. Although, you know, they do exist as well. So spin will find the more difficult types of things, especially in multi-threaded code. So this has no capability to do multi-threaded analysis. So spin focuses on concurrent code and finding race condition deadlocks and violations of requirements in a multi-threaded application. And this is more like the coding errors. So now, I've made this claim before, where if you look at where do developers spend most of their time when they do testing and bug fixing, I would claim 80%, 80 to 90%, they're coding errors. There's like, why did I miss that? So there's like a relational symbol pointing the wrong way, or there's a particular statement and assignment missing, things that are fairly shallow. The really deeper algorithmic errors are in the 10 to 20%. So this tool focuses on the 80 to 90% of the cases, like the more shallow types of defects, which dominate developer time and tester time. And spin is focused on the deeper things, the 10%. Now, one other thing I want to mention is, as you noticed in the demo I gave at the end, there's no GUI for this yet. Now, my experience with spin, the spin distribution, this much older, it is 20-some years ago. spin distribution, there was fairly little interest in the tool up to the point where I added a GUI, and then suddenly a number of people using the tool shot up to staggering numbers. So we're at this point for pre-GUI for this tool. Now, there's no GUI yet because I can't think of a good way to build that GUI. So basically, this is an engine that can sit as a background engine behind some, maybe Emacs, who knows, behind some interface. And if you have ideas about how to build an interface, this would be really cool to do. I'll probably come around to building a user interface for this at some point, where it's easier to type the queries and to see the results, but that hasn't been done yet.